So, Higher Maths Unit 3 Practice Assessment, NAB 3 if you like. Outcome 1, three-dimensional vectors. And for this outcome there are 12 marks available, and in order to pass it you will need to get 9 out of those 12 marks. Now this whole outcome is about vectors, and quite simply a vector is simply a quantity which has a magnitude and a direction, so that it could be represented graphically as a line of a certain length pointing in a certain direction. And for that reason, that can be referred to as a directed line segment. It's got a direction and it's only part of a line, the required length. Now, whereas vectors have got many uses in describing things like velocity and force and so on, here, as far as the higher is concerned, you'll be using them simply as a displacement, a movement from one point to another. That displacement, instead of drawing this all out, could be represented simply as a movement from A to B in this direction. Another alternative, if there are no starting and ending points, is simply to give the vector a name like u, for instance. Notice the little tilde underneath is meant to show that this is a vector quantity, in that it's got more than one number required to describe it. Now, as a displacement, that simply means how do you get from one point to another? In a coordinate system, how many along, and this is three-dimensional, how many along, how many back, and then how many up to get from A to B. Those are the three components: the x component, the y component, and the z component. How many along in the direction of the x-axis, how many back in the direction of the y-axis, and then how many up in the direction of the z-axis. Whereas this notation AB means to move from point A to point B, the usefulness of this notation is simply to describe that move so that's free to be made in any position, so that you can have a relative or an absolute displacement. Absolute meaning I'm starting at this fixed point and finishing at that fixed point, and this line only joins those 2 points. Whereas the move that was required to make that could be positioned anywhere. That would be a relative move from any point you care to use, and that's where it's handy to use this notation. U would stand simply for that move. So this vector u could be drawn anywhere else, as long as the distance is the same and the direction is the same, which means the components must be the same. So if I was starting from a point C and wished to have a point D which was in the same relative position to it as B is to A, I would simply use that vector u again to move me to this position. Now the first question in this involves this part of it. If I use the same components, I must move the same direction, the same distance in the same direction. That just comes from the two right-angled triangles that are involved there. Those two sides, using Pythagoras, gives me a certain length for this. And then those two sides using Pythagoras gives me the required length of that. And they must be the same in both cases because these two triangles are the same. Now these two triangles are positioned, the xy is in the horizontal plane, and the one with the z is in a vertical plane. And it's the same for the angles. Now in 2 dimensions, there's only one angle required to define the direction of a line. In 3 dimensions, in space, 2 angles are required. One for the amount you swing along the horizontal plane, and then another for the amount you swing up the way vertically. These 2 angles in here. And obviously if these 2 triangles are the same, then those angles must be the same. If you adjust these lengths in the same proportion, if you were to double each of those components, you would then travel twice the distance because you'd have doubled those Pythagoras calculations. However, if you were to have doubled those components, you would still be travelling in the same angle because the tangents of these angles just depend on the ratio of opposite over adjacent. So vectors will have the same length and the same direction if their components are identical. And vectors will have different lengths but the same direction if their components are multiples of each other. Double components, you'll have double the length but the same direction. Half the components, you'll have half the length, but the same direction. And that's what the first question is about. For the first question, you have to prove that 3 points are collinear. Now, these 3 points will be collinear if the move from A to B is a multiple of the move from B to C, because that would mean that those directions are the same. As an alternative to using A and B and C, although those are the best for finding ratios later, you could compare AB with AC. If those directions are the same, that would have to be a straight line, because otherwise it'd be hinged. But it's not enough to say if you have 2 line segments which are parallel, that means they form a straight line, because obviously in this case they don't. They'll only form a straight line if they're actually joined together at some point. So for this question, proving 3 points are collinear, there's 2 things you'll have to do. First, I'll have to show that the 2 line segments have got the same direction. That is, one vector is a multiple of the other vector, and then make the simple statement that since they've got the same direction and they're joined at the point B, they must form a straight line, they must be collinear. So here's an example then. Now this is a 4-mark question. The first part is just for saying what are the components of the move from A to B. Now, there's only 1 mark, and quite simply you could just state it by obviously looking at the moves required. You could simply say, well, I've gone from -1 to 5, so I've gone 6 along the x. I've gone from 2 to 5, so that's an increase of 3. And I've gone from 7 to 16, so that's an increase of 9. So that's the vector. And in truth, that's the way you would do it later on once you were used to vectors. But it'd probably be safer to make that other statement and derive the components of this displacement from the position vectors. Now, position vectors means this. If you've got a point A and a point B, and you want to know how to get from A to B, because this is the whole basis of many vector situations, the way you find an unknown vector is to follow a vector path you know. You know how to get to A from the origin, I've got its coordinates, and know how to get to vector B from the origin, I've got its coordinates. Well, the move that takes you from the origin to A is known as the position vector of A. Use a small case letter. The move that takes you from the origin to B, which is obviously the coordinates there, is known as the position vector of B. And a vector pathway to find AB means this. To find AB, which is the line segment I don't know, follow paths that you do know, starting at A and finishing at B, no matter how circuitous that may be. Well, one way to start at A and finish at B would be to retrace A to the origin, that would be -A, and then follow B to the point B, those being the known pathways. And that's the thing you'd probably write down first of all, used to seeing AB is B minus A. Although that's obvious, it's fairly trivial that it must be B minus A, because what are the moves required? It's this number, take away that number to find how far I moved in that direction. So as an alternative to just stating that for the first mark, you may wish to write B minus A, and then put in the components. 5, 5, 16, take away -1, 2, 7. To arrive obviously at the exact same answer, 5 take away -1 is 6, because there's 6 units from -1 to 5. 5 take away 2 is 3, 16 take away 7 is 9. You probably will be doing this all the time, and at the beginning it's probably safer, because even though it seems quite tedious to write all of this out when that's so obvious, what this does is it slows you down. It makes you think about each of the numbers twice as you write them, so you're less likely to make some clerical mistake copying the wrong numbers down. So this is what you would probably do at this level for that first mark. Now the second mark would be that, not the second mark, the second part's this for 3 marks. Show the 3 points are collinear. Well, let's just put them down schematically, it might not be in this particular order. Say that was A, that was B, and that was C. Now that just means that I need to show that the direction of any, and there's actually 3 line segments there. There's the 2 obvious shorter ones, and there's the longer one AC. I just need to show that any 2 of those are multiples of each other. The obvious ones are AB and BC since I've got AB already. You could do BC or you could do AC, that would also work, but I think I'll go for BC. I've got AB, so what's BC? Well, I'll just follow this route, C minus B. Again, you know what the answer is going to be, 5, that's 4, 5 to 7 is 2, and then that's 6. However, it's safer to do this to begin with. That would be 9, 7, 22, and 5, 5, 16, just because it slows you down and makes you think about the numbers. 9 take away 5 is 4, 7 take away 5 is 2, 22 take away 16 is 6. Now that would be the second mark for finding a second vector. Whether it was BC or whether it was AC makes no difference. Now the next stage is to show that those are multiples of each other. Now if they're multiples of each other, that means each of the components must be the same multiple. So it's safer just to compare each of the components. What are the components? If I want to write my statement as AB is some multiple of BC, then it'll be AB divided by BC, components, that is. So I'll just do that here. So 6 compared to 4. Is that the same as 3 compared to 2? Is that the same as 9 upon 6? If those fractions are all the same, and they are, they all cancel down to that 3 upon 2, then that's the multiple you've got. If one of them was different, it'd be no use. So now I can make the statement, well, AB is 3 upon 2 times BC. That's the second mark out of these 3 marks. Now the last part's a bit tedious because, as I said before, you can't say, there you go, they're collinear. You have to make several statements. What does this imply? If one vector is a multiple of another vector, that means that the line AB is parallel to the line BC. Probably safer to write as parallel. I'll just use the symbol. AB is parallel to BC. That's not enough to guarantee they're collinear. I can have 2 parallel line segments, but they might not be joined. So now I've got to make this statement. Since they're joined at B, since B is a common point.
Yes, there's no T in common. It's just that the whole phrase ended in an NT. It just took so long to write it.
Now I can say, if the lines are parallel and they're joined at B, that means that A, B and C are collinear. And you'll only get this last mark, this third mark from part B, if you make both of these statements. One, that they're parallel, or you could just say go in the same direction. Probably better to say parallel. They're parallel because they're multiples of each other. And since they're joined at B, that means they're collinear. So those are the 4 marks you get for question 1. Now question 2 is for finding a point that divides a line in a given ratio. So you'll be given 2 points. I'll just take this as an example. So you'll be given a line segment with the coordinates of the 2 endpoints, and you'll be required to find some point in between them, an internal division that cuts it in some simple ratio, and it will be really simple, something like 2 to 1 or 3 to 1. Where would the point L be that cuts that line in the ratio of, now it wouldn't show this in the diagram, I'll just say this in the wording. So say L divides KM in the ratio 2 to 1, which means going from K to M in this direction, it's 2 steps until you hit L, and then it's another 1 step to finish it off to reach M. Now unfortunately this is just a 3 mark question, and there are several ways of doing it, and the only one that's given in the marking scheme is the most oblique one. It's an algebraic version of it, which is actually quite lengthy and quite rote really, because you lose sight of the usefulness of vectors and vector pathways. I would say here that there's basically 2 different techniques you can use here. There's a vector pathways approach, which is visual and easily understood, or there's a formula called the section formula, which gives you this point straight away. Neither of those are shown in that marking scheme. They're down under other acceptable methods, presumably, though it doesn't qualify what they are. And it gives this other oblique one, which eventually takes you to the section formula halfway through it. The very first part of it is even a little bit rote, because the first part of it would be make a statement connecting KL and LM by saying, well, what's the connection between the move KL and the move LM? And it's something to do with this 2 and the 1. And you may well learn it as, oh, I just take those numbers and I put them the other way around. Why? Because you do. No, the reason is this. If the ratio KL to LM is 2 to 1, remember, that ratio is just another representation of the fraction. It means KL over LM equals 2 over 1. So that whatever those numbers are cross multiplying would give you 1 lot of KL is 2 lots of LM. That being a 1. If the ratios were something else like 3 to 2, then it would be 2 of them would be 3 of those. But you may well just remember that as, oh, that just goes to the other side. And that indeed is the first mark. Saying KL is 2LM, or whatever numbers are there that would cross over, gives you the first mark in this scheme. Now there's only 3 marks. That means if that's the first mark, and the final coordinates must be the third mark, then the other mark must be for all the stuff that goes on in between, which is just a nonsense, of course. So here's the first mark, and the procedure that they were looking for in the marking scheme would be this then, to say, well, what's KL? That's L minus K, subtracting the position vectors. What's LM? Well, that's M minus L. So rearranging all that, you've got what? L minus K equals 2M minus 2L. Gather the L's together. Minus 2 would come across here. Oh, I might as well put this down just to make it look even more ridiculous. So L plus the 2L is, now to keep them in the right order, I'll write K plus 2M. Well, that of course makes 3. Remember, this is the second mark. Well, that's the first mark. Even that first mark was a bit of jiggery-pokery. 3L equals K plus 2M. So finally, L is 1/3 of K plus 2M. That's worth no marks in the marking scheme because you haven't done enough yet. Now the whole point about this is, this thing here, which has taken all of this time to arrive at, is the section formula. Which is a valid starting point for the question. Instead of writing this down, if you were presented with that question, you could just jump straight in using the formula. L equals, that's the position of this point of division, would be 1 over the sum of the parts, that's 2 parts and 1 part is 3 parts, times, and then with the same reasoning as that, it would be 1 lot of K plus 2 lots of M. Section formula, instead of all of this. So if you were doing this question, I would say, using the section formula, that statement would be the first mark. Now the whole point is, after this, both of these are going to be identical. Whether you go in with the section formula or whether you start with this equation of line segments. These will be the same for this following part. So back to this. So writing this down would be the first mark. Going through all of that, you would arrive at L is 1/3 of K plus 2M. You know it's going to reach that because that's the section formula, and that's where that goes. This algebraic technique would take you to the section formula. I don't see any reason why you can't just go straight in with that. That's what you would do in exams. That's what you see in marking schemes in exam. After that, for the second mark, it's a case of putting in all the numbers, but even that isn't enough to get the second mark. So K would be -1, 2, 0, plus 2 lots of 5, 11, 3. The second mark comes from, according to the scheme, to start evaluating the components. So it's not sufficient just for the substitution, there has to be an evaluation. It seems to indicate to do this part. So you've got 10, take away 1 is 9, 22 and 2, which is 24, 6 and 0, which is 6, which of course then gives you, and this seems to be the point at which the second mark is obtained, start evaluation. Then finishing that off, dividing by 3, you've got 3, 8, 2. But then It's a coordinate it's looking for, not the position vector of L. So for the final mark then, just write that sideways as a coordinate, 3, 8, 2, and there's the third mark. Now that's one way, using this equation of line segments, going through the algebra to arrive at the section formula, and then doing the arithmetic. Or I would think just starting with the section formula and then doing the arithmetic. Those should be equivalent, those two statements. That's one way, that's an algebraic way, that's a formula. The other way is to use vector paths and say this. How do I get to L? Well, to get to point L, that's from the origin, wherever it is, how do I find L? How do I find the position vector of L? Follow a path I do know. Well, I know how to get from 0 to k, so that'd be k. And I know how to get from k to m, because I know those. And L happens to be 2 steps out of the 3. L happens to be 2/3 of the way from k to m. That's the statement I would put down. So I would guess that that would be the first mark for making that vector pathway statement, which is nice and clear and easy to visualise. How do you get to L? Go to k, then go from k to L. And that happens to be 2/3 of the way to m. Then I'd put in the numbers. So k was -120 plus 2/3 of, and since it's only worth 1 mark for this arithmetic in the middle, you could do km by inspection. You could work it out at the side if you like by km is m minus k, or you could just easily say -1 to 5 is 6, 2 to 11 is 9, 0 to 3 is 3, and you know if that's correct according to the question, if those numbers divide by this denominator, because they would be meant to in this particular case to keep it easy. So that, what would that add up to? So 2/3 of 6 is 4, take away 1 is 3. 2/3 of 9, 3 into 9 is 3, is 6, plus 2 is 8. And 2/3 of 3 is 2, plus 0 is 2. So there you are, it's the point 3, 8, 2. So that's the third mark. I much prefer this method because it's completely visual. Where would the marks be allocated? I don't know, because there's only 3 marks. Obviously that's worth a mark because that's the initial pathway. Obviously that's worth a mark because that's the answer. So somewhere in here the second mark appears, and that second mark would probably be in this line, probably for making this statement here, because remember that was a derived one. You'd maybe be better just working that out at the side, even though it becomes a bit annoying. 5, 11, 3, take away -120 equals, obviously the same thing, 6, 9, 3. It just makes this look more cumbersome to put in here. This is a much neater looking approach. Still, that was question 2. Now the third question for 5 marks is that nice one that you want to get in the actual exam. Find the angle between 2 vectors. You'll be given 2 vectors as displacements. Say for instance, I've got I, j and k. You'll be told those displacements, like this for instance, and the question in 2 parts would be, first of all, find ji dot jk, which means the scalar product of those vectors. Now the scalar product of 2 vectors is a product in that it is a multiplication of them. It's a multiplication of their lengths, but not the lengths as they stand just now. It's the multiplication of the projection of one length onto the other. If I draw them down here, that was vector A and that was vector B. The scalar product of AB means the length of A that goes in the same direction as B, as if you were shining a light down straight onto it. That's the projection of A that lies in the direction of B. So it's not all of the length of A. Remember, the length of A you show between those 2 modulus signs. Whatever the angle happens to be, this side adjacent to the angle would have this length over A, making the cos, the part you need, so that that length would be A times the cos. That's the projection of it, the amount that goes in the same direction as B. It's just the same as if you had a track and some object had to be moved along this track, and A represented the force that was going to move it. Well, obviously, the direction of that force will influence how well it will move along that track. The best direction to apply the force in would be along the direction of the track, and then all of the force would be used to move it. The worst direction would be at right angles, because then it wouldn't move at all, because no component of the force is going in the right direction if the point has to stay on the track B. So it's the component, it's the projection of one vector onto another. The length of one, it is a product, the length of one times the length of the other, the projection of one. So it's the length of A in the direction of B times B. Well, you would just say the length of A times the length of B times the cosine of the angle in between them. Now that's one way of working out the scalar product. There's another way of working out the scalar product if you happen to know their components. If you happen to know the components, then the scalar product is simply the product of the components, x's, y's and z's, scalar. Scalar means the result isn't a vector. Scalar means a single number. So the scalar product would be the product of the components added together. 2 times 4. So let me just put it in this way. 3 times -1. 5 times 2, but all added together. Multiply the x's, the y's and the z's and add them into a single number, a scalar. Scalar product. So it would be 8 take away 3 plus 10, 18 take away 3, 15. The scalar product would be 15. Now that also means if you were to multiply the length of this by the length of that times the cosine of the angle in between them, the answer would be the same thing, 15. And that's the way you do part B. Now that's just worth the 1 mark there. Part B says, what's the size of the angle IJK? Well, it's done by the 2 methods for the scalar product. I can either do the scalar product by multiplying the components, or I can do the scalar product by multiplying the lengths. And of course this involves a cos theta. And to work out the length of a vector, that's just Pythagoras in the 3 dimensions, because the 3-dimensional vector has got the horizontal triangle with x and y, use Pythagoras in that, and then the vertical triangle with that squared hypotenuse added onto that squared side to give the final one. It's Pythagoras in 3 dimensions. So you know everything apart from this, so you can find that. So what would the statement be? I would say, well, ji, the length of ji times the length of jk times the cosine of the angle in between, ijk, Caesar used the little hat symbol for angle there, is one way of working at the scalar product, is the same as ji dot jk. Now that's the equivalence of the scalar products, but you'd probably start off question B, not with that statement, but with the statement rearranged just to say the cosine. You'd probably start off by saying cos ijk equals ji dot jk, that's the scalar product, divided by the length of ji times the length of jk. That would be the first mark, just for making that statement. Now there's 3 bits in this formula. There's a scalar product, you've got that already, so there's the 2 lengths to work out. And marks 3 and 4 are for working out those 2 lengths. There's a mark for each of those parts, so you might as well set it out the NAB mark way. So what about the length of ji? Well, that'll just be the square root of, it's just Pythagoras, so instead of squared I'll just do the square root of the square of the components. So that's going to be, and there's only 1 mark, so you could either write 2 squared plus 3 squared plus 5 squared, or you could jump straight in with 4, 9 and 25. Well, we'll just play safe. 2 squared, 3 squared and 5 squared. That's 4 and 9 and 25. So that's going to be 38. And the length of jk will be the square root of 4 squared, -1 squared and 2 squared, which is 16 and 1 and 4, which is the square root of 21. Now those are worth a mark each, whether you write them separate at the side or whether you've got that working in here. So putting that together, that means that the cosine would be 15 divided by the square root of 38 times the square root of 21. Now there's 5 marks altogether. The final mark, because we've got 4 already, won't come until you get the answer. So there's no point trying to evaluate this. You can simply go straight in and say the angle IJK will be the inverse cos of that, and just enter it in that form into your calculator. Or instead of putting the square root down twice in the numerator, remember to use that fraction button. Instead of putting the square root, you can just put the square root of 38 times 21. Then, putting it into your calculator, you get the answer, 57.927 and so on. So we'll call that 57.9 degrees, and that's the 5th mark. Now try the 3 questions yourself. So for question 1, here are 3 points P, Q and R. First of all, get the components of PQ, and secondly, show that P, Q and R are collinear. Well, the first part, you could always put a little schematic down for it. Just put them down, it might not be their correct orientation, but then you can't show the correct orientation in 3-dimensional space because it depends on your viewpoint. So, if those are the points P, Q and R, the first part says, what are the components of PQ? Now, you could state that straight away. P to Q, but sometimes when they're all over the place like that, it might be safer to slow down and say, oh no, where to put this? PQ equals Q minus P. This makes you take care to make sure which one's which. So Q is the second one here, negative 648, and P is the first one here, negative 402. If of course you'd taken time to put the numbers down in this diagram, you would need to do that really. Which gives you negative 6 plus 4 is negative 2. 4 take away nothing is 4. Oops. And 8 take away 2 is 6. That would be the first mark. Second part, show they're collinear. Well, now it's up to you. Will I compare that line segment with the line segment QR to show that they're multiples? Or will I compare PQ with PR and show that they're multiples? I think I'll just go for the obvious one, which is the QR. So QR, what's the move from Q to R? Well, that would be R take away Q. R being the last mentioned, which is negative 7, 6, 11, and Q being the second one, negative 6, 4, 8. So that would be negative 7 plus 6 is negative 1. 6 take away 4 is 2. 11 take away 8 is 3. That's the second mark from question 1. Now what's the connection? Are they multiples? They're only going to be multiples if their components are all the same multiples of each other, if their components form the same ratios, form the same fractions. If I want to make my statement saying PQ equals, then I'll divide the PQ components by the QR components. And I'll just double check at the side what that is. So I've got negative 2, how does that compare with negative 1? And 4 with 2, and 6 with 3. Do all those fractions cancel to the same number? Yes, they all cancel exactly to 2. Which means I can make the statement that PQ is 2 times QR. All the components are 2 times. In which case, that means that the line PQ is parallel to QR. I'm tempted just to use the symbol, but maybe I'll just play safe and write it in words, is parallel to QR. That's not sufficient for the last mark. 2 parallel lines don't need to be joined, so I have to make the statement that says, yes, they are. Since Q is a common point, I can now say P, Q, and R are collinear. And that's the final mark for 4 marks altogether. No, I forgot to indicate that the third mark, which was this statement here. There's the 4 marks. Now number 2 for 3 marks, which is the annoying one marks wise, because there are 3 techniques you could use. There's the equivalence or equating the line segments. There's the section formula, which would be a more sensible alternative to equating the line segments, or there's the pathways. If I start off with this part, notice it just says at the side B divides AC in the ratio of 3 to 1, which means it's 3 steps from A to B and then another 1 step on from B to C. That means that this line segment AB over that line segment BC is 3 over 1. So one way of doing this question would be to say 1 lot of AB is 3 lots of BC. That would be the first mark. And then go through all of B, Maths certainly would never ever do it this way. Then go through all of B minus A is 3 times C minus B. Do you put numbers into this point or just carry on with the algebra? So that's B minus A is 3C minus 3B. So that means that I've got, bringing that minus 3B over, 4 lots of B is bringing the A over A plus 3C. Then you could put in the numbers here at some point, and then finally divide by 4, or just make the statement B equals a quarter of A plus 3C. But of course, that's the section formula, which would seem a much more obvious point to start at, using the section formula to find point B. 1 over the sum of the parts, because there's 4 parts altogether, and then 3 lots of C, 1 lot of A. The same crossing over that you do in this part here. The 3 goes with the C and the 1 goes with the A. So, see no reason why you couldn't simply jump straight in with that for the equivalent first mark, instead of going through all of this. Then continuing, simply putting in the numbers. So you've got 1 quarter of, well, A was 5, 1, negative 2. C is 9, negative 3, 10. No marks yet. Carrying out this calculation seems to be where the second mark is. 1 quarter of 32, negative 9, negative 8, 30 take away 2, 28. That's, I reckon, whereabouts the second mark is, which then gives you, and of course one check is they should all divide. If they don't, then they've done something wrong as far as that NAB's concerned. 4 into that's 8, 4 into that's negative 2, 4 into that's 7. That's not the final mark because it wants the coordinates, not the components of the position vector. The position vector of B is that. It's the coordinates of B which are required, so simply write those on their side. So B is 8, negative 2, 7 for the third mark. Now the other way would simply be to say, well, I want the point B, so how do I get there? How can I get to that point B? Well, I know how to get to A, so I'll start at A, and I know how to get from A to C. B's along that route from A to C. It's 3 out of the 4 parts, 3 steps, 1 step, 4 steps. It's 3 steps out of the 4 steps, so it's 3 quarters of AC. That would be the equivalent first mark then, for that pathways, that vector statement. Then, putting the numbers in, what have we got? A is 5, 1, negative 2, plus 3 quarters of, and since I've got this diagram here, I can see quite clearly where I'm starting and where I'm finishing, and it's not as if those coordinates were jumbled up in a question and I had to decide which numbers go to which. I think I could just do this AC by inspection. 5 to 9 is an increase of 4, 1 to negative 3 is a drop of 4, negative 2 to 10 is an increase of 12. Now, where does the second mark come? I'd be tempted just to do that in 1, but if I split that, it might make it similar to the calculation halfway point in the previous method. Do this multiplication here, 3 quarters of 4, 3. 3 quarters of negative 4, negative 3. 3 quarters of 12, 9. I would say that would be the second mark. Adding them together, 5 and 3 is 8. 1 take away 3 is negative 2. Negative 2 plus 9, as before, is 7. For the position vector. So finally, what's the point B? 8, negative 2, 7 for mark 3. Then number 3, scalar product, angle between two vectors. Here it's quite clear, there's just one technique, which is going to be equating the two methods of finding the scalar product. Well, what's the scalar product? What part A says for 1 mark. If you've got the components, that's the simplest way of finding it. Multiply the components and add them. So what is the scalar product? It'll be the 3 times the 1, the product of the x's, the 0 times the 2, the product of the y's, plus the 1 times the negative 2, the product of the z components, not being 3 separate components in a vector, but being added together to make a single number. So what I have is a 3 plus a nothing, take away a 2, which is just 1. There's the first mark. Second part, how do I find the angle between two vectors? Well, the first thing is, if you require the angle between two vectors, make sure you're using the components of the vectors that point away from a common point, because that is the definition of the scalar product. The projection of one vector onto the length of the other vector. Depends which way they're facing. If I had a case where it was the vector ML projected onto it, well, K looks like this, but ML would be a vector if I move it into position over here, and its projection would go in the opposite direction. But that was taken care of in the question anyway. So with this you would go in with the formula, and yes, it is a formula because you're equating the two methods. So you'd start off with the cosine of KLM is the scalar product, which you've just done. Suppose you could get away just by writing 1 down because I've already done all of that. Divided by the lengths of the same two things, LM, LK, LM, LK. Now I'd be tempted just to put it all down here, but since I've already worked this out, normally you'd have all the numbers appearing here. The scalar product, the length, then the answer. I'll just work them out at the side then. What is the length of LM? Well, it's the square root of the components. It's the square root of 3 squared plus nothing squared, or 0 squared, plus 1 squared, the square root of 9 and 0 and 1, which is the square root of 10. That's the mark. What is the length of LK? Well, it's the square root of the components of 1 squared and 2 squared and negative 2 squared. So that's the square root of 1 and 4 and 4, which is root 9. Now, strictly speaking, it doesn't matter if that becomes 3 when you use it in your calculation. But since it's so obvious, I think I'll go to 3 in this case. That's another mark. Putting it into this formula, it would read 1 over root 10 times 3, which means that KLM for the angle would be inverse cos of that thing, 1 over, and I'll just change them into 3 root 10. Don't think I put down the fact that that formula there is 1 mark. Last marks then, just for putting that into your calculator. And that gives you 83.949 and so on, which I'll call 83.9 degrees for the 5th mark.